Hello everyone, how are you all? Welcome back to Diksha Karnataka YouTube channel. Today I am going to discuss the PU2 Midterm chapter current electricity, and first we are starting with theory revision. After theory revision is over, there will be a video for 1 marker MCQ questions as well as 2, 3 and 5 marker questions, all questions which are important from this chapter. Now, before I begin with this chapter, some students do requested to do this chapter as early as possible. It was not possible to give this chapter at the second, but I am giving this chapter as third. Few things I want to talk about this chapter, that this chapter is important in terms of theory as well as numerical questions. Now if you practicing numerical questions from this chapter, then only you should try it. I will be solving numerical questions from this chapter, worry not, but I personally do not recommend this chapter's numericals for medium to below medium students. Those who are very good at numericals, they should definitely try numerical questions from this chapter, because not only it will help you to solve questions in your long-term PU exam, also it will help you to score well in JEE and KCET exam. KCET level numericals we will do later on sometime, but in midterm paper, if you are practicing regularly from this chapter, very good. Otherwise you can skip numerical questions from this chapter. Also if you want to answer one question from this chapter, if you are starting to solve numericals from this chapter right now from this midterm, then by the time you appear for your PU, you will be able to answer this question. It requires a lot of practice for answering the questions from this chapter, not theory questions. Theory questions are easy, I will discuss that as well, but in terms of numericals, questions are slightly tricky. Last year paper was also again some tricky question came from this chapter. Anyway, you should keep it as a backup, but should not be your primary target. Now let's start. Let us look into the list of important chapters from this chapter. Electric current, definitely Ohm's law, resistance and resistivity, drift velocity, combination of cells, and KCL and KVL. Also KCL and KVL means it also includes as an application Wheatstone bridge. Okay, now let's start with electric current. So the net amount of charge Q, net amount of charge Q is flowing across the area in the forward direction in the time interval t, then the current is. So if the current that is flowing in the forward direction in the time t, charge flowing is Q, then what is current? Current is basically defined by Q by T, right? So total amount of charge divided by time is current. But that definition, this definition is somewhat old. We have learning this definition since class 6 or 7. So let us now change it a little bit to be a PU2 level definition. So currents are not always steady, and hence more generally we define current as limit delta t tends to 0, delta q by delta t, that is dq by dt. So this is the PU2 level definition. This is class 6-7 level definition. Okay, but in 99.99% cases this definition will be more important than this definition, but yes, in some cases this definition can also be useful. Now electric currents in conductor. So electric charges experiences a force in the presence of an electric field. We have already learned about this. Charges kept in an external field, it will experience a force. What is that force? That force was given by just a second. That force is given by F is equal to Q into Q into E, right? So electric charge Q kept in an external electric field E, it experiences a force Q into E. Okay, what next? Electrons being negatively charged move opposite to the direction of electric field. Metals having a large number of free electrons, these electrons accelerate in the presence of an external field. Now metals have free electrons, obviously charges move normally, right? Now charge means electrons are also charges, they will also move. Now metals they are basically called sea of electrons. Sea, if you go visit a sea, you will see a lot of water in that sea, right? Similarly, a metal is basically has a lot of free electrons inside it. Now those free electrons, when you apply an external electric field across the conductor, they will also start to move in the direction opposite to that of applied electric field. Very important point to remember. This gives rise to the electric current. So you have a conductor, and if you apply some electric field, then the electrons which are present inside the metal, they starts to move in the direction opposite to that of the applied electric field. Normally if the electric field is not there, these electrons are moving randomly. These electrons are moving randomly like gas, right? But if you apply an electric field, then as soon as you start applying electric field, they will start to move in the opposite direction. Random motion will still be there, but apparent total motion, there will be a total motion in the opposite direction. We will come to that in a little while. Okay, before that, let us discuss about Ohm's law. Okay, if temperature and other physical conditions remain same, the current I, so we have discussed what is the source of current. Now let us understand a bit the relationship between current and potential difference. Okay, if temperature and other physical conditions remains the same, the current I through a conductor is directly proportional to the applied potential difference. So V is proportional to I. Okay, and if you remove the proportionality sign, it gives you V is equal to IR, the very common, very well known formula of Ohm's law. Now here you have to remember that there are few questions that comes, what are the constants of Ohm's law? So the constants of Ohm's law is temperature and physical condition. Physical condition means physical state. There are 3 states of matter mainly. Okay, in fact there are right now 5 states of matter universally accepted, but you can say for our own purpose 3 states of matter. Okay, so 3 states of matter. So if they are called physical states, right? So if physical states remain same, that means if you are passing a current through a solid, the solid will remain solid. Okay, then this Ohm's law is valid. In case suppose you applied a lot of current and the solid melts into a liquid, then Ohm's law will no longer be valid. Okay, the constant of proportionality R is called the resistance of the conductor. The resistance R not only depends on the material of the conductor, but also on the dimensions of the conductor. So R depends on material of the conductor and the dimensions. Dimensions means length, height, width, they are called dimensions. So dimensions of the conductor and the material of the conductor, it is independent of voltage and current, right? So R is basically independent of voltage and current, but it is dependent on the dimensions and the material, right? There is another form of Ohm's law which is given by J equals to sigma into E. So we said that current starts to flow when you apply electric field. That's why the definition of current density, here J is called current density, sigma is called conductance of the conductor. Obviously conductor means it has a higher conductance. So this is the conductance and E is the applied electric field. Now if you plot a V versus I graph, how to plot a graph? You take one variable, plot it along x-axis, you take the second variable, plot it along y-axis. Okay, for suppose 10 volt, 10 ampere is the current, so 10 volt and 10 ampere becomes a point, and you collect all such points and then draw a line. You will observe that the V versus I graph will always pass through origin, and if the, obviously not always, but for a ohmic conductor, the conductor which is obeying Ohm's law, the current will always, current versus I graph will always pass through origin and it will be a straight line graph. It will be a straight line graph. If it is not a straight line, curved line, then Ohm's law is not valid. It is not obeying Ohm's law. And remember that not everything has to obey Ohm's law. There are a lot of exceptions in that matter. Okay, but normally all the conductors, metal conductors, they obey Ohm's law. Okay, now let us look into resistance and resistivity. Resistance is directly proportional to length of the conductor. So longer the path, higher is the resistance. But by the way, if you don't remember what is resistance means the friction. It's kind of electric friction that it provides when electrons are trying to move through a conductor. So if electrons are trying to move through a conductor, it is being opposed by some property of the material, so it is trying to stop that electron. Okay, so higher, if the resistance is very high, then electrons will not be able to move through the conductor. If resistance is low, electrons will easily move through the conductor. Now higher the resistance, higher the length, higher is the resistance. Next, higher is the cross sectional area, lower is the resistance, right? Inversely proportional. Inversely proportional means if this quantity is higher, this quantity is lower, and vice versa. Okay, now combining these two equations, we can write R is equal to rho L by A. Here rho is called the resistivity of the conductor. Rho is called the resistivity of the conductor. Sometimes it is also called specific resistance. Specific resistance. Same thing. You learned about specific gravity. Okay, you also did some experiment on specific gravity, right, in your first PU. Maybe you ignored that chapter, that is a separate story, but I remember you have done some experiment on specific gravity bottle or specific gravity of stone after immersing it into water, right? So those kind of experiment you have done. So specific gravity is there. Here it is called specific resistance. It is not a resistance, its unit is different, okay, but it is sometimes called specific resistance, just a different name for you to remember. Now unit of resistivity is ohm meter. Resistivity is independent of the geometry of the material. It varies from material to material and on temperature. So resistivity depends on two things, material and temperature. So for example, for say silver resistivity is say X, for copper resistivity is Y, for gold resistivity is Z. So it varies from material to material and temperature. If you use the same temperature, the resistivity for a given material will be constant. Okay, it does not depend how long, how wide is, but resistance do depend, resistivity not. That's why the term specific resistance. Now resistivity, how it is depends on temperature. This is the basic formula, not important for PU board, just for your understanding. Okay, and its unit is ohm meter. Now drift velocity. So we said that when a conductor is kept in an electric field, okay, or if you apply an electric field across a conductor, the electrons starts to move opposite to the applied electric field. Okay, they are still moving in a random motion. Random motion is still there. Okay, random motion is still there, but even with the random motion is slowly shifting in the direction opposite to the applied electric field. So random motion is still happening. Okay, random motion is still happening, but this they are doing this random motion and they are still moving in the opposite direction of the applied electric field, which is very, very interesting, right? So it's like a moonwalk. Okay, so the electrons are doing moonwalk and they are moving backwards, right? If you don't know moonwalk, what moonwalk is, you should go and Google it. What is a moonwalk? Okay, there is a famous person who is famous for his moonwalk. Okay, now anyway, so drift velocity is that average velocity. Drift velocity is the average velocity with which it slowly moves in the opposite direction of the applied electric field. Okay, the expression for drift velocity is given by minus EE by m into tau. Why this is minus? Because charge of an electron is negative, that's why this Vd represents, the negative sign represents the direction of drift velocity and that of the electric field are in opposite. Velocity is a vector quantity, electric field is also vector quantity. So this negative sign represents that if electric field is on the right, then drift velocity is on the left. That is the significance of this negative sign. Now what is the expression for current? Current is given by NEA Vd. Here Vd is basically the modulus. Okay, here we take the modulus value of NEA Vd, scalar form, scalar value. Only value is important in this expression. Now if you see that current, basically current through a conductor depends only on drift velocity. The random motion or the thermal motion, it does not depend on this current. Current only depends on drift velocity, current does not depend on thermal motion. So if you heat up a metal, okay, and if you apply some electric field, the resistance will change, the value of current will increase or decrease, but it will not depend on the random motion of electron or thermal motion of electron. The velocity, the current will change based on the number of availability of electrons. So this value will change. This is the number density of electron. What is the meaning of number density? Number of electrons per unit volume. Okay, n is number density of electrons. Remember these terms, it will be helpful for you to solve some questions where you will be able to identify what are the quantities. That's it. So n is number density, E we know, charge of an electron, A is area of the conductor. Now you have to also remember one more thing, that drift velocity into area is constant. That means suppose a current is flowing through a conductor having different cross sections. The cross section of this side, say A1, drift velocity is Vd1. Suppose area of this side is A2 and drift velocity is Vd2, then A1 Vd1 will be equals to A2 Vd2. Okay, so this is what one more important property of drift velocity. Next, mobility. Mobility means how the electrons are moving, how quickly the electrons are moving against the applied electric field. Okay, if the electric field is strong, definitely electrons will move, but if electric field is weak, how quickly the electrons are moving, that is a measure of mobility. And this one more term, this tau, this is the relaxation time of electron. Relaxation time means like when you are studying one book, then you are closing the book, you are watching some reels, then again you are studying some other book. So the time where you are watching the reels is basically the relaxation time, right? Similarly, the only job of electron is to collide with another electron or with another atom. Electrons have no jobs, they have only one job, that is find a target and hit it. Okay, the target will find itself, so their only job is to go and collide with other electrons and other atoms. So between these two collisions, whatever time the electron has is called the relaxation time. During that time, electron can relax and move in a straight line. Like for you, you are watching some reels, right? Once this lecture is over, before the next lecture starts, you will scroll some reels, right? Then you will remember, oh, Soumikshar has another class, I have to come back and join that class, then you will come back, right? Now mobility is defined as, again, modulus of drift velocity divided by applied electric field. So if the value of mobility is higher, that means you can generate a large current using small electric field. Okay, and its exact value is charge of an electron, relaxation time divided by mass of electron. Here m is mass of electron. Okay, and resistivity is given by, this is not actually resistivity, this is conductivity. Resistivity is opposite to that of that, this is conductivity. Okay, so let me add one smart thing. This is resistivity. Conductivity and resistivity are exactly opposite to that of that. Inverse of resistivity is conductivity. So conductivity is given by n e square tau by m. Now these formulas are not, all the formulas are not important. This is a must remember formula, okay. And sometimes these derivations they might ask you, there are some instances where they have asked these derivations, especially mobility derivation, okay, but it is easy, derivations are easy, not difficult, okay. Don't study all the possible derivations, okay. Some channels, some teachers, they recommend all the derivations, but this I is equal to NA VD derivation is important, and from here, starting from this formula, deriving J is equal to sigma E, that is also another important derivation. We will do that. We will do that in the 2, 3, 5 mark lecture session. Now limitations of Ohm's law, as I said, Ohm's law is not always correct. So V ceases to be proportional to I. The relationship between V and I depends on the sign of V. So these are the few examples you have to remember. There are some diagrams. If you are interested in detailed study, you can go to Sankalp channel. There I have done a detailed analysis of all the properties. Okay, the relationship between V and I is not unique. That is, there is more than one value of V for the same current I. So these are the major 3 limitations of Ohm's law. So what is the meaning of limitations? Limitations means you cannot apply Ohm's law in these 3 cases. Now combination of resistances, I hope everyone remembers it. Series combination, the easiest one, R equivalent is equal to R1 plus R2 plus R3 plus so on. Now in the series combination, remember that current is same through all the resistors, okay. Current is same in all the resistors, okay. And in parallel combination, again the same value, 1 by Req is equal to 1 by R1 plus 1 by R2. In parallel combination, voltage is same, okay. Also for two resistors in parallel, we can write as R equivalent equals to R1 R2 by R1 plus R2, right? Remember this. Now you have to also remember that I have seen students while solving parallel combinations questions, they solve the right hand side properly. In the left hand side, what they do, they forget to take the inverse. So you have to take the reciprocal on both sides. Reciprocal on both sides is very, very important, essential to find the final R equivalent. Now electrical energy and power. So basic formula for energy is given by vitamin. Energy is vitamin. If you eat vitamin, you will get energy. Okay, so energy is VIT, voltage current into time. Okay, voltage current into time is the energy that is radiated in a device. Suppose you have a resistance, you have a battery connected across it, so the resistance is basically spending energy, right? It is basically the device which is spending energy. For example, if you switch on a light bulb, the light bulb is basically spending energy. The energy that it spent is given by VIT. Remember, energy equals to vitamin. Okay, then it will be very easy for you. Now power is H divided by T. So it is Vodafone Idea. Sometimes we will use I square R or V square by R. Okay, VI, power is Y. Okay, Y, you can remember Y, you can remember Vodafone Idea, whatever you are comfortable with. Now electric cells combination, this is also tumba important. Cells in series, epsilon, if they are in series, basically gets added, as simple as that. Resistance get added, EMFs get added, but remember that here all the cells are connected in the particular exact same order. If the order is changed, then one might be negative as well. Anyway, cells in parallel cells is little tricky. This is the easiest formula to remember. Remember this is the easiest formula to remember. There is another formula given in your textbook, okay, that final formula you can remember very good, but if you are someone who get confused very quickly, then epsilon 1 by R1, epsilon 2 by R2, epsilon 3 by R3, add them, divided by 1 by R1 plus 1 by R2 plus 1 by R3. This is the most easiest formula to remember. and R equivalent for parallel, obviously same formula for parallel. So this is how you can remember this cells in parallel. Now in both cases, this case and this case, the current, the ultimate current in the circuit is given by I equals to epsilon equivalent plus this is the external resistance connected in the circuit and this is the total internal resistance. Okay, from there you can calculate the current that is passing through the circuit. Now Kirchhoff's rules, there are two Kirchhoff's rules, junction rule also called Kirchhoff's current law or KCL. At any junction, the sum of currents entering the junction is equal to the sum of current leaving the junction. Junction means where multiple currents meet, that is called a junction. Okay, suppose I1 and I2 going in and I3 going out. So according to Kirchhoff's law, I3 equals to I1 plus I2. Now this is nothing but conservation of charge. Okay, this is nothing but conservation of charge. If you multiply all the currents with time, you will get charge, right? So if Q1 charge is coming from this side, Q2 charge is coming from this side, Q1 plus Q2 charge should pass to the third line because it's an isolated system. So in isolated system, the total charge should be conserved. That is basically the Kirchhoff's current law. This is a direct consequence of conservation of charge principle. Next is loop rule or Kirchhoff's voltage law called KVL. The algebraic sum of changes in a potential around any closed loop involving resistors and cells in the loop is 0. Okay, the law is based on the conservation of energy principle. Now on this law we will be solving numericals. It is very important for solving numerical questions. So we will be apply this rule and learn a little bit more about this rule, but sometimes this comes as a mark question, 1 mark, 2 mark, 3 mark question. So understand this, and this is an important statement for these two are an important statement for MCQs and fill in the blanks. Last concept of the chapter, Wheatstone bridge. Wheatstone bridge is a device which is basically used to measure unknown resistances. How it can be achieved? To achieve that, we have to first achieve a specific condition called balanced condition. Okay, balanced condition of Wheatstone bridge. So here we have a battery, 4 resistors connected like this peculiar format, and there is a voltmeter, which is or galvanometer basically, which denotes the current is flowing in this particular junction. Okay, now what is the meaning of balanced condition? In balanced condition, there is no current which passes through this galvanometer. If you can somehow make current passing through this galvanometer to be 0, then this condition is called balanced condition. That means all the arms, they are called arms of a Wheatstone bridge. Okay, this is 1 arm, 2 arm, 3 arm, 4 arm. It is like the 4 arm Ben 10 character. If you are someone who used to watch Ben 10, when I was a kid, it was one of the famous shows, animes, right? So these are the 4 arm of the Wheatstone bridge. So you can say that so once this balance condition is achieved, the arms are basically in a particular order, that is P by Q equals to R by S. P, value of P divided by value of Q must be equals to value of R divided by value of S. This is the balanced condition. This is known as balanced condition, and this is the required condition for that the Wheatstone bridge will be balanced. So you can say that if the bridge is balanced, this must be the case. If this is the case, then the bridge must be balanced, vice versa. Okay, so this is the one of the most important derivation for your PU board as well as in your midterm. We will do the derivations, and there are cases, instances, for example 2024, one numerical question in board exam, one numerical question came from this chapter, exactly from Wheatstone bridge, which was not balanced by the way. So that type of questions you might face as well. right? So we will be solving those questions as well as the derivation, this Wheatstone bridge derivation, which is very, very important. Apart from that, obviously the series and parallel combination of cells are important, not resistances. Series and parallel combinations of cells are also important derivations from this chapter. We will be doing that very soon. Don't go anywhere. I'll be back with MCQs very soon. Till then, bye.